All right. The next thing we're going to end up talking about relates to what we did previous session, where we talked about Faraday's law of induction and some of the consequences of that. And at the very end, we ended up talking about how a solenoid can end up being used to induce an alternating current, which we'll talk about alternating current a little bit later. But I want to talk a little bit about something else that can happen with a solenoid. So if you end up having current that ends up coming into a solenoid, we already talked about before we had this 2-week break thing that we had, that the magnetic field is produced inside of the solenoid. We need to talk a little bit more about the direction. We didn't really worry a lot about that before. Suppose you've got current that comes into a solenoid from below and comes out above. It turns out, if you end up following the way the coil runs in here, that the coil will end up turning around in a particular way. And sorry, this is my right hand, even though it's on the left side. So whenever I end up doing following the coil around, my thumb will end up pointing in the direction that the current will be. So the current ends up going in the same direction as you would get if you replaced the coil with just a straight line. So the current would go through that way. That's the direction the magnetic field will point whenever you end up having a magnetic field through a solenoid. The next thing to remember is that we said that the magnetic field is almost exactly uniform. It's not perfectly uniform, but we're going to end up, for this purpose, assuming that it is. And again, all that ends up doing in some cases is modifying one of the numbers that we get, which we'll talk about in the inductance of something a little later. That's how we end up dealing with that. Okay, so we have that idea. Now we also know what the formula is for the magnetic field inside here. It's mu0 times the number of turns, right? The number of loops that you have, divided by the length. The length up and down, and then times the current. What we want to then look at is what happens whenever I have a current that flows through. I want to think about the magnetic flux. And the reason why we have magnetic flux is, remember that if your magnetic field is going this way, we've got the turns in this direction. So my area vector points the same way. So the dot product is not zero. In fact, it's going to be maximal because they're parallel. So I end up having a magnetic flux that's induced by having the current going through it. And to end up computing what the flux itself is, it'll be the integral of your B dot dA. Your magnetic field inside there, we will end up saying is constant. It's not perfectly, but it's reasonably close. So if we assume that it's constant, we can factor it out of the integral, as you end up seeing inside the derivative on the one loop EMF in the notes. Then the integral of dA is the area, like we've done before. So then the dot product is the magnitudes multiplied together times the cosine of the angle, but they're parallel to each other. Magnetic field and the area vector are both this way, so the angle is 0, cosine of 0 is 1. So then we can end up plugging in now what my magnetic field magnitude is, which is mu0 n over L times I times the area. And so then your EMF is minus the first derivative of the flux, and so that you can end up following that on the notes. Then to end up finding the total EMF, just like what we did with the alternating current, same idea. If we've got n turns, then we end up multiplying the amount of EMF through one turn by however many of them are stacked up. So we multiply by n, and you end up doing the arithmetic, and you end up getting that formula down there at the bottom of the first page. mu0 n squared over L times your area times the first derivative of your current. And if you don't deform the solenoid, so if you don't change the number of turns, you don't squeeze it in together, you don't change your cross-sectional area, you don't do the slinky thing while stretching it, you don't do any of those things, then all of those terms at the beginning are constant. So that's the reason we can factor all of that stuff out of the derivative, and we get mu 0 n squared over L times A as being a constant that's multiplied by the first derivative of the current, and we call that whole mess the inductance of the coil. And inductance of a coil is simple to compute. Mu 0, again, remember, is now approximately, but really close to being exact, is 4 pi times 10 to the negative 7th. Number of turns squared divided by the length times your cross-sectional area. That's all you do to find your find your inductance. And I believe I ended up setting up a really easy assessment question for you to end up going through and just explicitly computing it. But it's literally just plugging and chugging. There's no special weirdness that you get with that. And so by cleaning all that up, we end up having then the EMF is just minus your inductance times di dt. Inductance, you can end up reasoning out from the formula, would have units of volts seconds per ampere is one way of writing it. There's a whole pot full of other ways you can, but it has a special name for that unit. It's called a Henry, so capital H. Just like a capital F is farads and all those others. So in terms of what that formula means, it is important to remember there's a minus sign. And what the minus sign means, just like before, is your EMF is set up in a way that opposes a change. And it's trying to oppose the change in your any change in the flux. And the flux is proportional to the current. So if you increase the current, then that will end up producing an EMF that tries to oppose that effect. It doesn't win, but it does try to oppose it. So in that situation, you end up getting an EMF that ends up causing the current to end up going downward from what you'd expect otherwise in the circuit if there wasn't anything there. And that's one of the reasons why this effect is called a back EMF. So it ends up, if you try to have current that changes through the coil, remember a current that stays fixed, there's no first derivative. The first derivative is 0. So if you have a constant current that's going through a coil, nothing happens. If you have a current, you have a magnetic field inside, but you're not going to get any back EMF. You only get a back EMF if the current changes, if it ends up becoming different over time. If your current is changing, then you will end up having an EMF that's generated that tries to push back against the way that the current was coming through. And a scenario where this is something that you would have seen before, if you have had the experience of being in a house and the air conditioner turns on. In that situation, you notice that the lights dim for a little. It doesn't stay dim, but dims for a little bit, and then it slowly ticks back up to being fully bright, as we will see when we talk about alternating current, but it's similar to what you already would expect from what we've talked about with direct current, because we've seen how bulbs in a lab can do with direct current. It's the same deal that you get with alternating current. There's a little bit of technicality in terms of why it works that may be a little bit more complicated. But you end up getting that back EMF that causes the potential difference that's coming into your house to temporarily go down. So if you have less potential difference that's coming in, your voltage technically, and we'll worry about the difference later. But whenever that number decreases over that short period of time, that's the reason that your bulb's dim, because then the potential difference is through all the stuff that's parallel. which would include the lights that are coming into your house. And so because the potential difference is less, you get less current, and you've seen in the lab that if you have less current through a filament, you're going to end up getting less light, right? So that's the reason that happens whenever you get when you have a kick on of something, and that the reason why we can also talk a little bit about this. The reason why a motor will need to have a coil, we now have enough to be able to understand it. What happens inside of a motor is that you have to have something to end up causing something to turn, of course. And in order to cause something to turn, you end up needing to have something that will respond to current that will cause something else to move. And what you can cause to move is if you have a permanent magnet set up and you end up sending current through a coil, then you end up having a magnetic field, and the magnetic field then can end up orienting due to the change in current. And so due to the current going through, excuse me. So as we get current that goes through, you end up causing a realignment. Then you have another permanent magnet, another realignment, another one current, and it goes around the loop, which is how you're able to get something to turn. And you end up needing to have, that's the reason why you need to have coils to end up doing that, which is why you want inductors at all. I mean, otherwise, we'll talk a little bit later that an inductor coil will store energy in the current, but that ultimately isn't terribly useful if you don't have something that you're trying to do with it. But that's the reason why we would want to end up having one of those in the first place inside of a circuit. We will talk in the next little bit about what happens whenever we hook up a resistor and an inductor. So we've just had an inductor. It's been a little bit hand wavy. We'll be able to get more explicit numbers in the next bit.